Hello, welcome to chapter 8. Oh my goodness. So in this chapter, we are talking about confidence intervals. So before I get into that, let me just start off with this little comic here. So I thought it was funny because this is kind of talking about like weathermen and like how they predict the weather. So this weather person is basically saying the high temperature will be between 40 below zero and 200 above zero, which, oh my goodness, of course they're going to be right. This guy's never wrong, because what kind of temperature will we have that would not be between those two temperatures? But however, is that actually helpful for us? I don't know, because when we talk about confidence intervals for this chapter, it's an interval of numbers. So like that's the mathematical term here. Interval, like an interval of numbers and a range of numbers, really, basically. We're trying to see whether we can use like this range of numbers or calculate this range of numbers to kind of predict. So in the past, in chapter 7, we were kind of looking at sampling distributions and talking about within a sample, what is the mean or what is the true proportion of that sample compared to the population. Because we were trying to look at the mean of a sample to see if it matches, if it's like a accurate predictor of the whole population itself. And so now, or back in that chapter, we were mostly given what that population mean or what that population proportion was. In real life, though, how would we know? How would we know that number without taking like a census or something like that? So the population parameter is not something that we get to just know. So we are starting to get a little bit more realistic with our situations now. So in this chapter, what we're going to be doing is using like a range of numbers to try to predict or to like describe what we think the population parameter is. So we're going to use a range of numbers to be like, okay, we think the population mean is going to be between these two numbers, or we think the population proportion is going to be between these two numbers. And we're going to use a sample to try to help us predict those two numbers. So that's what we're using confidence intervals for. So the general method of calculating this range of numbers is kind of using this really general formula. And we'll get into the more specifics of it in our section 2 and section 3 of this chapter. But for now, we've got a couple new vocabulary words in order to use this formula. So the general formula is that we're going to take the point estimate, and really the point estimate is just another name for the sample statistic. So let's say we're talking about averages. If we took a sample, found the average of that sample, we're trying to use that sample to predict for the population. So that sample's average would be considered the point estimate. Because remember, a sample statistic is like the number from the sample. Or if we were doing this with a proportion, then the proportion of that sample would be considered our point estimate. Then we're using that as kind of like our central number, and then we're going to add and subtract the margin of error. And so margin of error, most people have at least heard the word before. Margin of error is used a lot, like if you hear on the news around election time, oh my goodness. Whenever they do polling of like who they think the candidate is currently winning, whatever, they do margin of error. So really, a margin of error is kind of how much we might be off by due to chance. So when we say due to chance, it's not because like you took a sample poorly or anything like that. It's just, the general variability when you take different samples. Your different samples are going to be different from one another. And so this margin of error deals with that variability where it's just due to chance. And so this, how much we might be off by, is kind of giving ourselves room for error. Because when you take a point estimate, some number, plus or minus this margin of error, that'll give you, two numbers for your range of numbers, our interval. And so that kind of gives us a little bit more accuracy, because we have more chance of being right when we actually have a range of numbers. Because like the weather people, when we say something like, oh, tomorrow's high is going to be a high of 81 degrees or something like that, then if the temperature tomorrow is actually higher than 81 degrees, then the weather person would be wrong. But if you can say something like, oh, I think the temperature is going to be between 79 degrees to 83 degrees tomorrow, then you have more chance of being right. Because if the temperature actually got past 81 tomorrow, you'd still have some room for error. And so you would still be considered correct. And that's what we're aiming for. That's why we want an interval of numbers so that we can try to predict accurately. When we calculate confidence intervals, we also talk about a confidence level. So I know it sounds very familiar between a confidence interval and a confidence level. They're completely different things. So a confidence interval is that range of numbers. A confidence level is basically describing like how confident are you in your prediction. So we use percentages to describe how confident we are. Like 100% confident versus like 75% confident, where you're like not as confident, but yeah, your math checks out. So we actually don't talk about being 100% confident because there's always room for error. So we don't deal with 100% confidence, but we will go up to like 99% confidence or like 99.9% confident just in case. Looking back at this comic from Garfield, the weather person says that they think the temperature, or they're stating the high temperature tomorrow will be between 40 below zero and 200 above. So notice how like this temperature range is huge. But Garfield then thinks this guy's never wrong because like, yeah, for sure. If you are making such a big range in your prediction, you can be super confident that you're going to be correct. So like this could be something like 99.9% confidence, where that 0.1 not confident is like if some crazy asteroid hit the Earth and the temperature went berserk, something like that. But when that confidence level is super high, we tend to need a wider confidence interval, like a bigger range of numbers to actually feel more confident, because that wider range of numbers will give you a higher chance of you actually being right. So a lower confidence level tends to come when your confidence interval is smaller because you have a lower chance of being correct. However, we actually want that interval to not be so wide, because how helpful would it be if I said, I think the average height of people is between 0 inches and 200 inches? Because obviously I would be correct. Everyone's heights are between 0 inches and 200 inches. But like that doesn't actually help me in gathering information about how tall people generally are. So we want like a balance between the confidence level, like we want to be confident, but we also need to make sure that interval of numbers is actually usable and helpful for us. So if we were trying to interpret a confidence level, basically what it means mathematically is that if we think back to our sampling distribution. So remember, in a full population, we could gather samples, like all the different combinations of samples of a certain size n or whatever. And out of all those samples, we can calculate that sample statistic, whether it's the average, the proportion, whatever we're trying to calculate. So out of all those different samples that we can make, all the different combinations of those samples, we would each calculate their mean or their proportion, and then add and subtract that margin of error, which we'll talk about how to calculate later on. But that means for each of those samples, we can actually calculate that confidence interval, a range of numbers. So the confidence level mathematically says that a certain percentage of all of those confidence intervals that we calculated from all the different possible samples, that percentage of confidence intervals would actually capture the true population parameter, the true population mean, the true population proportion, whatever it is, blank percent of those intervals that would get calculated would actually include the true parameter. So let's say the true population height, average height, is 65 inches. I don't know, like half the world doesn't even use inches, but whatever. So let's pretend that in all of the world, the true average height is 65 inches of like adults or whatever. Then when we go and look at the sampling distributions, let's say we were talking about sample sizes of 1,000, something like that. So for every single different combination of samples of size 1,000, when we calculate those confidence intervals, we're going to get all sorts of crazy numbers because each sample that we take, the mean's going to be slightly different because means that include, a bunch of shorter people is going to have a smaller mean than, or a sample that includes a bunch of shorter people is going to have a much smaller mean than a sample that had, like, for some reason, a whole bunch of tall people, that mean's going to be higher. So there's going to be differences. But then when you calculate the margin of error, that plus or minus, now that your range of numbers, some of them are going to include that 65 inches that we were talking about. Some of them will not. And so the confidence level talks about what percentage of those sampling distributions, of those confidence intervals, are actually going to include the true mean. And so, again, very abstract concept here because that's not something we can actually do in real life. But our confidence level, mathematically, that's how it's described. What percent of all of the confidence intervals would actually capture the true population proportion or true population mean? So we also want to be able to interpret the confidence interval itself. So remember, the confidence interval is that range of numbers. So when we interpret it, we're basically saying we are blank percent confident, and that percent confidence is always something that's going to be given to you. They'll tell you in the problem what percent confidence you want to use. We are blank percent confident that the true mean or proportion, depending on the problem, you're going to choose either the mean or proportion of whatever the context is between blank and blank. And those are the numbers that you would calculate and fill it in with that. So again, a lot of my interpretations were trying to make it so that you just fill in the blank here. And so everything that's underlined is something that you should be filling in. So now let's actually get into the calculation of the confidence interval a little bit. We're not going to get fully into the formulas just yet. There's a part that I want to show you first. So earlier we talked about how the confidence intervals are calculated with a point estimate plus or minus that margin of error. So the point estimate, there's really nothing, no formula for that. That's just from the sample, what was your mean or what was your proportion, whatever from your sample. That should be something that's given to you, or you can calculate yourself. Then the margin of error part, that's the part that we're really going to have to focus our calculations on. So the margin of error part is really this, a critical value, and I'll explain what that is, times the standard deviation of the statistic. So both of these things multiplied together make up the margin of error. And this right here is actually the formula that's given to you on the AP Statistics formula sheet. So they'll give you this, but to me it's not that helpful because it doesn't actually give you the specifics of the formula. But what I will teach you today is how to find that critical value first. So we talked about how the statistic is something that's given to you in the problem. It's the sample mean or the sample proportion. The standard deviation of the statistic, this you actually already know how to find. This is the standard deviation of the sampling distribution. So if this was the proportion problems, then the formula would be the square root of p times 1 minus p over n. Or if this was a mean problem, a sampling mean problem, then it would be the sigma divided by the square root of n formula. So that's the standard deviation of the statistic. The critical value is based off of the normal curve. So if you remember our sampling distributions where, we had the new formulas for the standard deviation, the sampling distributions were based off of a normal curve as long as we did that large counts condition or the central limit theorem to check to make sure it was actually normally distributed. So because we're basing that off of the normal curve, our critical value is basically saying in the sampling distribution, we're trying to see that range of numbers. Can it be centered around here or something like that? Or, over here if we're on the proportion side. So depending on which type of problem we have, we would be using the normal curve to find like how big of an interval that we want. And the size of that interval then depends on this critical value. So this critical value is based off of z-scores, because z-scores relate to our normal curves. So when we calculate the z-score, we're basically saying this is the confidence level I want in the middle of my normal curve. And then our critical value, our z-score, we actually denote it using a z-star to show people like this is specifically for confidence intervals. So it's a z-score still, but it's for confidence intervals. So we're going to be trying to find the z-score where the percent confidence is what's in the middle of our normal curve. And let me do a few examples. So let's say we're asked to be 90% confident. So we're going to end up calculating a 90% confidence interval. So based on the normal curve, we want 90% in the middle because our range of numbers from here to here for our confidence interval, we want to be that wide. And so to calculate that z-score of these two endpoints here, if 90% has to be in the middle of our normal curve, then that means 10% has to be on the outsides, which means on each side of the normal curve, each side has to be 5%. Okay, so remember, under a normal curve, the total should be 100%. So if 90% is in the middle because we want 90% confidence, then 5% should be on each side. So we're going to use these numbers to calculate our z-star, our critical value. So keep in mind, like if you're using the table only tells you values that are on the left side, like shaded to the left. So we're basically looking at our table the backwards direction. We are given a percentage, this 5% right here, and we're looking for the z-score that corresponds. So looking in your table, for a number that's closest to 0.05 in the middle, there's actually two that are equally distant from each other. You should see a 0.0495 and a 0.0505. So the two z-scores that those correspond with is a negative 1.64 and a negative 1.65. So because they are exactly the same distance away from both of them, we'll actually average those two z-scores out to get negative 1.645. Like if you add the two z-scores and divide by 2 to find the average. So the z-score that has 5% on each side is going to be negative 1.645 and positive 1.645 because, you know, in a normal curve, it's symmetric on both sides. So if one side is negative, the other side has to be positive. So when we're finding that critical value, the z-star, we always use the positive number. So it'll be 1.645 positive. The reason why it doesn't matter technically if we use positive or negative is if you look back at our formula, it's technically plus or minus and then whatever those two numbers end up multiplying to be. So when you multiply, and it doesn't matter whether it's positive or negative, let's say we got positive, you're still going to be adding and subtracting that positive number. If you get negative, you're still going to end up being adding and subtracting that negative number, which just does the opposite. So the positive or negative doesn't actually matter. So just as a general rule, we like positive numbers better. So we always use positive numbers for our critical value. Let's do another example. So let's say this time we're trying to find 95% confidence. And this is actually the confidence level that's used the most common one. So 95% confidence means that we want 95% in the middle, which means 5% has to be on the outsides of our normal curve. So if I split that in half, that would make 2.5% on each side. So now looking at the table, if we're trying to find 0.025, the number that's going to be closest is going to be, I think, 1.96 or negative 1.96 as the z-score. So that means Z star for us is going to be positive 1.96. Up until now, I've been using the table to find these critical values. If you are a calculator user because you appreciate the quickness and the speed that the calculator allows, you would be using the inverse norm function. So normally to get to normal CDF to calculate our probabilities, we would go second vars and then the, your upper, lower, blah, blah, blah. So if you look right under normal CDF, you'll see inverse norm. So second vars number 3 is inverse norm. Inverse norm asks you for the area and then the mean and the standard deviation. So because we are calculating our z-scores, the mean and standard deviation is always 0 and 1. 0 for the mean, 1 for the standard deviation. The area is basically asking, what's the shaded area to the left over here? And it's always to the left. When you type it in, also make sure that you are using decimals and not percentages. So for like 95% confidence, you should be typing in 0.025 for the area, 0 for the mean, 1 for the standard deviation, and then that'll give you the Z star of, I think the calculator is much more accurate. It does 1.9599 or something like that. So this is where I'm going to kind of leave you for the calculation of the confidence intervals. We will get into more detail in our future sections when we can actually be more specific about whether we're talking about proportions or means, and that way we can use that to actually practice finding our confidence intervals with numbers involved. But thanks for watching. Don't forget to like and subscribe this video, and I'll see you next time. Bye.